Well, hi again, this is Bob, and I'm over on page 332, and you may recall I decided to break this section into two parts. One of them was to introduce some applications for the data tables in different situations, how we can apply our data tables, our standard normal distribution, to make predictions or to find percentages and probabilities, etc. And we're going to kind of go backwards a little bit now. We're going to find a data value. And remember, in our formula, we have a formula for the z-value, which is our given data value, subtract the mean, divided by the standard deviation. Well, we're going to see some situations where we want to find the given data value, okay? And it's not really a difficult derivation to find that. One way that you could do it would be to multiply both sides of the equation by the standard deviation. This would give you the z-value times the standard deviation equals the data value that we're interested in minus the mean, and then we could simply add the mean to both sides. And it turns out that the z-value times the standard deviation plus the population mean would be equal to our corresponding data value. Okay, well, we don't have to derive it, and we don't have to call it up each time. We can just use the book's definition, which is basically, I just kind of repeated what they did for finding an individual data value. It's the z-value times the standard deviation plus our population mean. Okay? And this is and they call that finding formula for finding the value of a normal variable x. So we're talking about a situation that has a normal distribution, where obviously, since we're talking about a z-value, we're talking about our standard normal distribution tables. And then they tell us now we're going to have two of many possible situations that we could apply this formula to. But first of all, at the bottom of page 332, they give us kind of a laundry list of what to do. And as always, the first thing they tell us is draw a normal curve and shade the desired area that represents the probability, proportion, or percentile. Then we find the z-value, which corresponds to that desired area, and then we apply this formula here. Because we will have a z-value, we will have a standard deviation, and we will have a mean. What we don't have is our variable, x. Okay? So I'm going to work both questions or both examples that they give us on this particular skill, and they start on page 333. And we already know the math, and if you recall, I emphasized in 6.1 how to go from an area to a z-value. Most of 6.1, we went from z-value to an area, but it's equally important to be able to go from an area to a z-value. So I'll talk as carefully as I can through through the two examples that they give us, and then we're going to finish off on this section learning about there's actually a formula that can tell us if we can use these standard normal distribution tables. And it has to do whether the data, either in frequency histogram form or in just the raw data, fits a certain equation. Anyway, let's look at example 6.9. This is the perfect type of example for this situation. It's a police academy qualification, and in order to qualify for a police academy, candidates must score in the top 10% of general abilities test. Okay? Now, the first thing when they say that, And there may be some other tests. I don't know the entire situation, but what they're basically saying in the top 10%, they're talking about this area right here, where 10% of the area, obviously that's the top 10%, because this would be where the mean is, smack in the middle, and the other 90%, if the top 10% is what we're interested in, then the other 90% would be to the left of this 10% here. Okay? Now, it may turn out that there are other requirements, physical type requirements, or testing requirements, or mental examinations, or so many different things. But I guess this is one of the first qualifications, is that you must score 10% on a general abilities test. Okay, so in order for us, now they give us some other information here. They tell us that the scores are normally distributed. That means that we can use our curve, and of course that means we can use our formula. And they tell us that this test has a mean of 200. I'll redraw it on the next page, and a standard deviation of 20. Well, check this out. We're going to be able, we've got an area, top 10%, that will allow us to find the corresponding z-value. And since we'll have the z-value, so let's try to write a check there, and the standard deviation and the mean, we can sort of work backwards and find that cutoff score. Okay, so it's got to be above 200 because 200's the mean. So let me redraw the situation. And of course, you've got the book in front of you there. Our mean is 200, and that's like having a z-value of 0. And what we're looking for is this cutoff score. This is one way to represent it, that represents the top 10%, and of course the other 90% would be to the left. And I'll label this again here. Now, we need to find that z-value, and so what we do, remember, if this is the top 10%, then it means that 90% of the graph is to the left of that 10%. And what we're going to do is we're going to go into the tables and we're going to find the closest value to 0.90 or 0.9000, if you will. It's 0.9 with or without the decimals. And we're going to find its corresponding z-value. And they tell us that when we do that, and this is directly below the question here, that the closest value that we find is 0.8997. And when we go up and when we go over, this is directly below the question there toward the bottom of page 333, we end up with 1.28. We end up with 1.28 on the z column and 0.08 directly above it. So our z-value is 1.28. Well, the book has a little nicer organization than I do, but now we've got all the information that we need, and I'll plug it back in after I write the formula here. Okay, and you recall that our z was 200, our standard deviation was 20, or excuse me, I'll get this right here. Our z was 1.28, and our standard deviation was 20, and our mean was 200. This will allow us to determine that cutoff score, and this is used all the time in like situations. So it's going to be 1.28 times a standard deviation of 20 plus 200. equals our cutoff score X. Now remember, in this case, we're not finding the z-value. We're using our formula into a derived formula to find a given data value. And that given data value rounded to the tenths place is 226. So if our mean is 200, you've got to score 226 to be considered as a candidate. I'm assuming that there's some other tests that the candidates or potential policemen will have to look at or perform. Okay, well, let's go look at the next one. You can review that question there. And this one has to do with blood pressure. And they tell us that for a medical study, a researcher wants to select people in the middle 60% of the population based on blood pressure. Now let's see what that means. When you say the middle 60%, here's the mean, and what you're basically going to do to be in the middle 60 is you would be like 30% above the mean and 30% below the mean. This then, this area, if you will, would represent the middle 60%. So there's some information already. Now, I think you can see what's going to happen here, and keep in mind that the normal distribution has symmetry. In other words, if we find the z-value for the 30% above the mean, then it should follow that the z-value for the 30% below the mean is the same number, it's just its opposite. Okay, so there's some other things we can put on here that we know already. We know that the graph, 50% of the area of the graph is above the mean, and 50% of the area of the graph is below the mean. That's where they got the 0.20s there. Now that we've got some kind of an idea of what's happening, let's do the following. Let's find that average blood pressure is 120. Lost my pen. And when we say average blood pressure is 120, we mean the mean is 120, and they tell us that the standard deviation is 8. Okay? Now, what we're supposed to do here, find the upper and lower readings that would qualify people to participate in the study. So what we're looking for here, remember our formula says that X is equal to the our corresponding z-value times the standard deviation, keep losing my pen, plus the mean. Well, it's pretty clear right away that we don't have the z-values there, okay? But we can get the z-values. And in fact, it's pretty straightforward to get the z-value. If you notice, there is 0.30 and 0.30 and 0.20 or 0.80 of the area to the left of that z-value, that positive z-value. This area is definitely 0.80. So we can find it pretty straightforward by going into our tables and finding the closest z-value to 0.80. And obviously we're going to be using our positive z-tables because we're on the right side of the mean there. And the book tells us that when we do that, and this is again is on page 334, then you end up with 0.84. Now, if the area, now remember there's symmetry here. This is our symmetry line where our mean equals 120. It should follow that if the area, that 30% to the right of our mean gives us 0.84, that then 30% to the left of our mean would give us minus 0.84. Okay, and of course, recall those are z-values there. So z is equal to minus 0.84 and positive 0.84. Well, let's see. We've got our z-values, we've got our standard deviation of 8, and we've got our mean of 120. I'll summarize again what we're looking for on the top of the next page. We'll do it in terms of values now. Okay, each one of these is equal to 30%. We know that their z-values associated with that was 0.84 and minus 0.84. So what we want to do is we want to find the value to the right of 120 and the value to the left. And remember that those values now represent blood pressures. Okay, they're not z-values any longer. We're going to plug those into our formula, which says that our variable, and remember that's what we're working on here, finding the normal variable, equal to the z-value times the standard deviation plus the mean. Let's do that first for, I'll follow the book here. They call this one X1. So let's do it for X1 first. It's going to equal 0.84 times the standard deviation of 8 plus 120. And when they do that calculation, they end up with 126.72. That would be in like millimeters of mercury there. Okay, now if we wanted to find the second blood pressure value, it would be like minus 0.84. Keep in mind we're on the other side of the mean here, times 8 plus 120. And taking the book's word for it, that turns out to be 113.28. Okay, so to summarize, (120) is the average blood pressure. The middle 60% of the population's blood pressure would fall in between 126.72 and 113.28. And that is how the researcher would go about, I can write 60 or 60% here. That's how the researcher would going about selecting candidates. They would have to have blood pressures between those two values there. Okay, well, we've got one more topic here, and I know sometimes people have come into this class and they've had another statistics class or a little exposure to statistics. Sometimes they've had some statistics with a emphasis on psychology. And on more than a few occasions, one of the things that they were required to do, which we don't normally do in this class, is go out and survey a population about a given trait or occurrence, and then find the mean, median, and mode, and so forth, and then make some predictions based on that gathered information. Okay, and they would normally assume that they did a good selection of population, that there weren't any people in the survey, let's say, that shouldn't have been there. In other words, they did a good job of setting up the study and choosing candidates for the study. Okay, and then what they would do after they had their numbers is they would try to make some predictions or draw some conclusions. Again, I'm talking about some people that have had a class in psychological statistics, because those are a little different than our class. normally in our class, they're going to give us the information, and then we just go right to the problem. We don't design any studies. We don't go out and physically interview people or study occurrences, okay? And anyway, so let's say that you were asked to do your own study and to draw some conclusions, and let's say that you went out and surveyed 30 or more people or made 30 or more observations, and you had your data, and you wanted to see if your data, if you could use the standard normal distribution on your data, or to make predictions or find areas and so forth. Well, it turns out that there is a way to do that, and more than one way actually. And on the bottom of page 334, they have a little section called Determining Normality. And it's based on stuff that we've already done before. Okay, and there's even a formula down below there, and this is called the Pearson coefficient, I believe. Pearson coefficient of skewedness, and skewedness is something that we've seen in Chapter 3, and it has something to do with this formula here, where you take 3 times the sample mean. Remember now, we've gone out and done our own sampling, minus the median. In other words, you take your sample mean and subtract the median, and divide the whole thing by the sample standard deviation. Okay, and we've, of course, as always, we've got a really nice example question to show this with. But so what we need is the sample mean, we need the median, and we need the sample standard deviation. And it turns out that when we work this question, we're going to get a number. Okay, and if that number turns out to be less than or equal to 1, or greater than or equal to -1, then we can go ahead and use our normal distribution. Now, if it doesn't, then we can conclude that the data set was not normally distributed. Okay, so I'm not going to repeat and find out the values. We'll take the book's word on the values, but as always, they've given us a little roadmap here of things to do. And the first thing that they tell us is they've given us on example 611, and I think I gave you a couple of questions like this in the homework. They told us that a survey of 18 high-tech firms showed the number of days inventory they had on hand. Determine if the data are approximately normally distributed. Okay, so what they did is they did a frequency distribution, and then from that they drew a histogram, and you can see the histogram in figure 629. Now, you know what? That histogram kind of looks like it's bell-shaped. Okay, it kind of looks, but we really don't know. So let's take the values that the book did for us and check it for its skewedness by using the formula we just saw. And in order to do that, we need some values. Fortunately, the book has given us the values. They found out that the sample mean was equal to 79.5. They found out that the median, yeah, I keep losing this pen here. Was equal to 77.5. Remember, these are all been calculated for us, and they found out that, or they're giving us the fact that the standard deviation is 40.5. So this would be like our data box here. Okay, so what we're going to do is stick those into the formula they gave us on the bottom of page 334, and if we get a value that lies inclusive between 1 and -1, then we can conclude that that data is approximately normally distributed, and we can use our standard normal distribution to find areas and make predictions and so forth. So our Pearson coefficient would equal 3 times the difference of our mean, which is 79.5, minus our median, which is 77.5, all divided by the standard deviation of 40.5. You know, we really don't have that big a sample size, but that's fine. We'll, as we go along, be seeing more information on sample sizes and other distributions. Anyway, the Pearson coefficient turns out to be 0.148. Well, certainly 0.148 lies between -1 and 1. Okay, so since it's in that boundary there, if you will, or in that interval, then we can conclude, and I'm reading from the bottom of page 335, in this case, the Pearson coefficient is not greater than +1 or less than -1, so it can be concluded that this distribution is not significantly skewed. Obviously, it's not our perfect or idealized distribution where we have our mean and median and mode all at the same place, but it tells us that it's not significantly skewed. And another thing, for what we gain from that means that we could use our standard normal distribution tables if requested. Okay, well, I'm going to ask you I take that back. There was one last thing we're supposed to do here, and this is on the top of page 336. They asked us to check for outliers, and you may recall that we had a formula for checking outliers where we found the interquartile range. This is back in chapter 3 stuff again. And we multiplied that times 1.5. Oops. And we added it to the third quartile and subtracted that value from the first quartile. And any number that fell above or below those respective values was considered an outlier. Well, for example that we just did, example 611, recall again, they've already done the work for us there. Okay, they did not find an outlier, and recall that outliers can skew the data. Okay, so I'm going to close off here by asking you to look over example 612. Maybe you want to practice a little bit using that Pearson coefficient formula, but read over example 612. It turns out that in this particular example, the data is significantly skewed. Okay, anyway, I will be back shortly with 6.3. Thank you.